Sometimes in astronomy, the biggest things, well, they pose the biggest puzzles.
That's definitely true.
And today, we're diving deep into a cosmic head-scratcher that's been bugging astronomers for ages.
Yeah.
Why galaxy clusters, these colossal gatherings of hundreds of galaxies, stay so darn hot.
It's a fascinating problem. I mean, you've got these immense
It's-
structures, the largest in the universe, right?
Right.
And they're surrounded by gas that's literally millions of degrees hot, superheated.
Millions. Wow.
Yeah, and this gas, it emits X-rays. And you'd think, logically, emitting all that energy, it should cool down over time, lose energy.
Exactly. It's like leaving a hot cup of coffee out on the counter. Eventually, it's going to cool off. So the expectation was, okay, as this gas in the clusters cooled, it'd get denser, clump up, and start forming lots of new stars, probably right at the cluster center.
Makes sense, right?
It does make perfect sense. That was the whole cooling flow theory. But when astronomers actually looked, the reality was quite different.
Oh, so? Well, the cores of these galaxy clusters, they remain stubbornly hot. Just hot. And we don't see nearly as many new stars forming as those cooling flow models predicted.
So way fewer stars than expected.
Way fewer. And that discrepancy, that's the cooling flow problem. It's been a major enigma for, well, decades.
Okay, so a long-standing mystery. But it sounds like maybe we have some answers brewing. Maybe thanks to a new set of eyes in the sky.
That seems to be the case.
We're going to unpack the recent findings from Japan's XRISM satellite. That's the X-ray imaging and spectroscopy mission.
That's right. XRISM has given us a crucial new perspective on this, specifically from its observations of the Centaurus cluster.
Centaurus cluster. Okay. Where's that?
It's relatively nearby, cosmically speaking, about 150 million light years away, close enough to be a prime target for a really detailed study like this.
150 million light years. Nearby. Love it. Okay, so our mission today. Understand how XRISM's look at Centaurus might solve this cosmic hot cluster mystery.
Let's do it.
All right, let's unpack this. Tell us a bit more about this XRISM satellite first and the instrument that's giving us these insights.
Sure. So XRISM is equipped with a really sophisticated instrument called Resolve.
Resolve.
And what makes Resolve special is its incredible ability to measure the energy of incoming X-rays very, very precisely.
More precisely than before.
Oh, much more. This allows scientists not just to get the temperature of the X-ray emitting gas, which we could sort of do before, but also to measure its motion with amazing accuracy.
The motion, that's key.
It really is. Think of it like spreading the X-ray light out, almost like a prism does with visible light. That's what spectroscopy is, fundamentally. Resolve does this so well that we can see tiny shifts in the energy. Shifts which tell us exactly how that super hot gas is moving, even subtle movements.
So instead of just seeing a big hot static blob of gas, we can actually see, the dynamics inside the blob, what's really going on.
Exactly. We can see the flows, the speeds.
Okay, here's where it gets really interesting then. What did XRISM and Resolve actually find when they pointed at the Centaurus cluster?
Well, the key finding, the big headline, was the discovery of a fast-moving stream of this superheated gas. And it's flowing right through the center of the cluster.
A fast-moving stream, not just sort of drifting.
No, not just a gentle drift. This was a significant energetic movement happening right there in the core.
Wow. Like a river of, million-degree gas flowing through space. So how does that help keep things hot? Does this motion somehow stop the cooling?
That's where this idea of gas sloshing comes in.
Gas sloshing, okay.
Yeah, think about stirring a pot of soup, maybe. When you stir it, you distribute the heat, right? You stop one part getting too cold while another stays boiling.
Right, you even things out.
Exactly. And this fast-moving gas stream in Centaurus seems to be doing something similar, just on an absolutely massive cosmic scale. This energetic motion acts like a giant cosmic stirrer, effectively redistributing heat. It takes heat from the slightly hotter outer regions of the cluster and mixes it into the center.
So the center is constantly getting topped up with heat from the outside, counteracting the cooling from the X-rays it's emitting.
That seems to be the picture, yes. The energy loss through X-ray emissions is being, offset or replenished by this constant stirring motion bringing hotter gas in.
That makes a lot of sense. Actually, we have a quote here from Professor Nakazawa, one of the researchers involved, that seems to nail this.
Oh, yes.
He said, "The mechanism which stops the cooling of the hot gas of this cluster is a general stirring of the hot gas that supplies energy to the center from outside regions, thus maintaining the high temperature."
That sums it perfectly. It's a continuous cycle of heat redistribution driven by this large-scale motion.
And you mentioned other ideas before, like black holes maybe reheating things. How does this sloshing compare?
Right, so that other major idea was AGN feedback energy from supermassive black holes, active galactic nuclei, blasting out and reheating the gas. And that definitely happens and is important, maybe dominant in some other clusters. But the specific type of motion XRISM saw in Centaurus, its scale and how it flows, it aligns really well with predictions from simulations about this sloshing mechanism. It looks like stirring is the main story here.
Interesting. And this wasn't totally unexpected, you're saying, the sloshing idea.
Well, it wasn't entirely out of the blue, no. Computer simulations, the ones that model how galaxy clusters grow and evolve over cosmic time, especially when smaller groups of galaxies merge together to form these massive clusters, those simulations actually predicted this kind of gas sloshing.
So the merging process itself could kickstart this stirring.
Exactly. These mergers are incredibly energetic events. All that gravitational interaction can really churn up the hot gas, setting it into these large-scale swirling, sloshing motions. It's not just random turbulence. It's more of a coherent, large-scale flow driven by the gravity of the merger.
So the XRISM observations are not just potentially solving the cooling flow problem, but they're also kind of confirming our computer models of how these giant structures form in the first place.
That's a huge part of it, yes. It ties observation and theory together quite nicely.
What are the bigger implications then for understanding how galaxy clusters, evolve over billions of years?
Well, this high-precision spectroscopy, the kind XRISM's Resolve instrument provides, it's proving invaluable. It's not just about temperature anymore.
Right, it's the motion.
Being able to measure the velocity of the gas so accurately gives us these crucial insights into the actual physics, the dynamics that shape these massive structures. Professor Nakazawa also mentioned this. He said, high-precision spectroscopy will also help us to better understand how the massive structure of galaxy clusters evolves. And he added that it deepens our understanding, not just of the clusters themselves, but of the formation and evolution of large-scale structures in the universe as a whole.
So understanding these clusters helps us understand the entire cosmic web, the biggest picture out there.
Absolutely. They're key nodes in that web.
It's just mind-boggling, the scale. Okay, so we have this superheated gas, millions of degrees being stirred around. Where did all that incredibly hot gas come from originally? How did it get there?
Right, good question. So these galaxy clusters, they're held together by an immense amount of gravity, far more than we can account for just from the stars and the gas we see.
Dark matter.
Exactly. Scientists believe most of that gravity comes from vast halos of invisible dark matter surrounding the clusters.
Okay.
And it's these huge dark matter halos that initially attract and pull in the gas from the space between galaxies, the intergalactic medium. As this gas falls into the cluster's deep gravitational well, it gets compressed and shock heated up to those millions of degrees. That's the initial heating process, basically accretion heating.
I see. So dark matter pulls it in, gravity heats it up, and then this sloshing motion keeps it stirred and prevents it from cooling back down too much.
That's the emerging picture. And it's this gentle but powerful motion, as the researchers described it, this sloshing, that seems key to maintaining the heat balance long term. It's different from, say, more violent, maybe short-lived energy injections from black holes or something. This seems more sustained.
A continuous stirring rather than periodic blasts.
Seems like it, at least in Centaurus.
Fascinating. Now, for anyone listening who wants to really dig into the research paper itself, this work was published in Nature, dated February 12th, 2025.
That's right.
And the DOI, if you want to look it up, is 10.1038, CIS 41586-024-08561 laws. We should also mention the artist's impression that came with the research.
Oh, yeah, the visualization. It's quite helpful.
It really is. It shows the center of the Centaurus cluster. Yeah. You can see this sort of bluish color representing that hot flowing gas stream we've been talking about.
The sloshing gas.
Then the little white dots are the galaxies embedded within it, and there's this reddish-brown area depicted indicating slightly cooler gas right at the very core that maybe hasn't been fully mixed yet.
It gives you a good mental picture of the dynamics. And credit for that image goes to JAXA, the Japanese space agency.
Great visual context. Okay, so let's try and wrap this up. To bring it all together, it really sounds like this long-standing puzzle, this cooling flow problem, why galaxy clusters stay so surprisingly hot, might finally have a really compelling solution.
It certainly looks that way.
And it's thanks to the sharp X-ray eyes of the XRISM satellite looking deep into the Centaurus cluster.
That's the key takeaway, I think. The direct observation of this significant gas sloshing, this large-scale stirring, it provides a clear physical mechanism.
A way to redistribute the heat.
Exactly. Redistribute heat, offset the energy loss from X-rays, and explain why these cosmic giants don't cool down and pump out stars at the rate we originally expected.
And it's amazing how this discovery really highlights the interconnectedness of things in the universe. From these relatively subtle movements of gas, all the way up to the evolution of the largest structures we know. The cosmic web itself, like Professor Nakazawa said, it's bigger than just the clusters.
Absolutely. This observation, though focused on Centaurus, has potentially far-reaching implications for cosmology, for how we understand the universe forming and evolving on the grandest scales.
It really makes you think, doesn't it? I mean, consider how these seemingly gentle, large-scale movements, this cosmic sloshing, can have such profound effects. It's almost like how a really slow stir can keep a vast pot of water warm for much longer.
That's a good analogy. Slow but persistent motion having a huge cumulative effect.
So it leaves you wondering what other seemingly quiet, maybe large-scale forces might be at play out there on cosmic scales, subtly shaping the universe in ways we're only just starting to grasp.
That's a great thought to end on. There's still so much we don't know about the dynamics of the universe.